In this video, I want to prove to you that the circumference of a circle is indeed 2 pi. So in order to do this, we're going to use the arc length formula of parametric equations. So, first things first, we need to figure out what a circle would be as represented by a parametric equation. So just a reminder, a parametric equation is when x equals something, or x is defined by something, and y is defined by something else. So, in order to figure this out really easily, we can look at a unit circle, and obviously this one isn't filled in, except we know that we use the point cos theta comma sine theta. So this one would be our x would be cos theta, and then sine theta would be our y coordinate, right? Pretty simple. So it's safe to say that x is cos theta, and y is sine theta. So we've got this, and we know in our formula for arc length we need to know what the derivative of x with respect to theta is and what the derivative of y with respect to theta is. So we already got x and y isolated, so we can easily just take the derivative of both sides with respect to theta. So of x equals, and then we're going to take the derivative with respect to theta of cos theta. So this one's just going to be dx with respect to theta. And then the derivative of cos theta with respect to theta is just going to be negative sine theta. So we've got one of the pieces that we need to put in our formula. So we've got one of them. And now we need to know what the other one's going to be. So we've got y is equal to sine theta. So clearly we're just going to take the derivative with respect to theta of both sides. Derivative with respect to theta. So the derivative of y is just going to be dy with respect to theta, and then the derivative of sine is going to be cos theta. Cos theta. So now we've got both pieces of information that we need. So now what we need to do is we need to plug it into our arc length formula. So we know that arc length is equal to, and it's the definite integral definite integral over the interval a to b of root, and then we've got a big root, and it is dy with respect to, in this case, we're respecting to theta, but you could see it as like a t or something. That's another very common one. And this right here is our arc length formula. So we've got all the pieces of information we need, but the only thing that I haven't really clarified is what is our bounds. We've got our lower bound a and our upper bound b. So we're proving the circumference. We know that if we look back to our unit circle, we start at this we start at like the beginning at 0, but then as we go around, we go to pi, we go to 3 pi on 2, and then we eventually come back around to 2 pi. That is the same point, and that's over around that way. So we know that we're gonna integrate from 0 to 2 pi. There we go. And this is going to be the root. And then our first one, dy with respect to theta. So that one's going to be cos theta. So we've got cos theta, and this is squared, so it's cos squared theta, plus, and then we've got derivative of x with respect to theta, and this is negative sine theta. So a negative times a negative is going to be a positive, and then it's squared, so it's just going to be positive sine squared theta. And you should notice something right away, that sine squared theta plus cos squared theta, or in this case it's cos squared theta plus sine squared theta, it's really the same thing, we're just adding, that's going to be equal to 1 according to the Pythagorean identity. So this right here is all just going to equal 1. So we can continue and we can write this out again. Definite integral from 0 to 2 pi And oh, let me change colors there. From 0 to 2 pi of root, and then this is just 1 now. So of root 1. And oh, hold on, I forgot all of these. Don't forget to write your d theta for all of these as well. Well, obviously root 1 is just going to be 1. So then this could be rewritten as the integral from 0 to 2 pi of 1, which you don't really write, so you could have it could just be d theta, or it could just be a 1 there. I usually like to keep the 1 because it helps me visualize it a bit better. So we're going to continue with this. So now what's the antiderivative of 1? And then we're going to plug in 2 pi into what our antiderivative is and subtract it from the lower bound, which is just 0. So the antiderivative of 1, we're just going to add, since it's a constant, we just add the variable that we're respecting to. So that's going to be theta. So the antiderivative is just theta, and then we have to plug in a 2 pi and subtract it from our lower bound, which is 0. So that's just going to be equal to, well, obviously plugging in 2 pi for the antiderivative is just theta, so it's just going to be 2 pi minus, and then if we plug in 0 as theta, it's just going to be 0. So then this is just going to equal 2 pi. So 2 pi is the arc length. And we have just proved, using our calculus knowledge, that the arc length is, or the circumference of the circle is indeed 2 pi.